Okay, so what if the next giant leap for AI has nothing to do with code and everything to do with, well, physics? We're about to dive into a totally different way of thinking about computers, one that leaves the digital world behind for something way more fundamental.
But first, to see where we're going, you gotta understand the wall we're speeding towards. See, the incredible, just massive demands of modern AI are stretching our current computer designs to their absolute breaking point. We've basically created a massive traffic jam inside our chips, a bottleneck that's really starting to slow things down. And this bottleneck, it actually has a name. It's called the memory wall, and it's pretty much the main villain in this whole story. Believe it or not, it all comes from a design choice made way back, over 75 years ago, that's just now starting to cause some serious problems. Pretty much every single computer you've ever used is built this way. Just picture a chef, that's your processor, who has to constantly run back and forth to the pantry, that's the memory, just to grab one single ingredient at a time. Now, for a simple recipe, sure, that works fine. But for the gigantic calculations AI needs, this constant back and forth, this data shuttle, is just ridiculously inefficient. It burns a ton of energy and wastes a ton of time. It's just not sustainable. So what's the fix? Well, it's a complete flip in how we think about computing. It's called analog in-memory computing. And the big idea is, instead of fighting against physics, let's actually use it. The concept is simple, but honestly, it's profound. Just get rid of that data shuttle entirely by doing the computing right where the data is stored. And this right here is the heart of it all. We stop thinking in these rigid black and white terms of ones and zeros. Instead, we encode information directly into the physical state of matter itself. And AI's knowledge, its synoptic weights, becomes a real physical property, like how easily electricity can flow through a specific material. And once you do that, you can do the math inside the memory. So how in the world does that work? Well, it's all thanks to two of the most basic laws of physics you probably learned in high school. First, you've got Ohm's law. You apply a voltage, which is your input, to a memory cell that has a certain conductance, which is your AI weight. The current that comes out is automatically their product. Boom, multiplication done. Then, Kirchhoff's law says that all the currents flowing down a wire just naturally add themselves up. So addition, done for free. An entire massive matrix multiplication, the absolute core of AI, happens in one single elegant step. Now, to actually make this happen, scientists are messing around with a few different materials, or what we can call flavors of memory. Each one is a unique attempt to find that perfect way to reliably store information in the state of matter. So first up, we've got flash memory. You know the stuff, it's in your phone, your SSDs. It works by trapping electrons. And because it's been around forever, it's super precise. The catch? It needs a lot of voltage to push those electrons around, and it wears out kind of fast. So it's great for running an AI model that's already trained, but maybe not so great for the training process itself. Next, we have the high-speed challenger, Ferroelectric FETs, or FeFETs for short. Instead of trapping charge, these things literally flip the orientation of tiny atomic switches inside a special crystal. This is incredibly fast and super durable, and it works with low power. That makes it a really exciting candidate for training AI right on the chip. But of course, there's a trade-off. That switching can be a little random, which makes it harder to control with absolute precision. And our third flavor is phase change memory. Now this one is really cool. This tech works by basically melting and refreezing a tiny bit of a special alloy, switching it between a messy, glassy state that resists electricity and an ordered, crystalline state that conducts it easily. It's an amazing process where the final value is determined by the ratio of crystal to glass. So when you lay them all out side by side, you can really see the tough choices engineers have to make. I mean, there's no single perfect technology here. Flash gives you that amazing precision. FeFETs give you incredible speed and they last forever. And PCM, well, it's a solid, balanced, and scalable approach. It's a classic engineering problem. You've got to pick the right tool for the right AI job. But all these trade-offs, they kind of hint at a much deeper problem. Because every single one of these technologies relies on messy, real-world physics, they all share a common set of enemies, these universal challenges that are kind of like ghosts in the machine. You see, unlike the perfect, predictable, digital world of bits, the analog world is just inherently random and a bit unstable. You've got stochasticity, which just means there's randomness in every single operation. Then there's asymmetry, which means it might be easier to turn a value up than it is to turn it down. That can really mess with learning. And then you've got temporal drift, which means the values you store can just change all on their own, like the memory is slowly forgetting. And this drift, well, it's the biggest ghost of them all. It happens because these materials are often kind of frozen in an unstable state. And over time, the atoms just naturally settle down and relax, and that changes the material's properties. It's like a guitar string that slowly goes out of tune. For an AI, this is a huge problem. It means its hard-won knowledge just degrades over time and its accuracy drops unless you're constantly fighting against it.
So the big question is, how do we tame these ghosts? Well, the answer isn't just to build a better device. No, it's about building a smarter system, an entire ecosystem that's designed from the ground up to handle and even embrace these physical imperfections. This right here is the key that's going to unlock everything. If we want this to work at a massive scale, the whole industry has to agree on a common language. We need standards for how we talk to these devices, how we measure their weird behaviors, and how we make sure they can all play nicely together. And a huge piece of that puzzle is deciding how we physically talk to these analog chips. How do we encode the input data in a signal? For example, we could use pulse amplitude modulation, or PAM, where the voltage level of a pulse carries the information. It's super fast, but it can be sensitive to noise. Or we could use pulse width modulation, PWM, where the length of the pulse is what matters. That's slower, but it's a lot tougher against noise. Picking the right signal format is an absolutely critical decision. So really, the path forward is a full-stack solution. It means we have to define what an acceptable level of randomness is. It means creating standard ways and circuits to handle that drift we talked about. It means building smarter AI software that actually knows the hardware has flaws and learns to work around them. And it means using really clever circuit designs that can actually cancel out their own errors. So the real takeaway here is this. The big AI hardware revolution isn't going to come from finding one single, perfect, flawless device. No way. Success is going to come from building an entire ecosystem, from the software to the circuits to the standards, that's smart enough to work with the beautifully imperfect reality of physics. And that leaves us with a pretty cool question to think about, right? To build the next generation of truly intelligent machines, maybe we need to stop thinking only in the abstract world of ones and zeros, and instead first become fluent in the native language of the universe itself, the language of physics.